computer. So, hello everyone. Welcome one day more to the RH Online course. Today is day 8. So, we will, just one second. Okay, sorry. In today's class, we will learn how to adapt Bifrost simulation to RH format. As we said, this is a very useful simulation of code that is produced in 3D MHD model since a while ago. And for example, in my case, I have used it a lot. So I think it's very convenient to learn how to do it for this case, but also everything that you learn today can be applied to other codes or to other simulation runs. So in particular, we will focus on the enhanced network simulation run that was presented in Carlsson 2016. This one has been used a lot, in fact, in multiple peer-reviewed studies or publications. Personally, I also have used it a lot, and I believe it's a great run. So I think starting with this simulation run, it's going to be helpful and useful. Okay, so what we are going to do today is to go step by step, transforming each atmospheric parameter, and also learning a bit to some ways to check that the transformation is reasonable, and we are understanding how the atmospheric parameters are defined, and for example, the sign of the velocity. So trying to get an idea that when you do a transformation, you change things, and then you should double check that everything is in the format that we need for RH. Otherwise, things will get a bit messy. So then this is just mainly what I've said, that the main difficulty of the process is to change to the correct units and also define the proper convention and everything else. So we will do it, and we will see that I have some ways that I always follow to just check that everything seems consistent. And as I said before, these things we will apply directly to the Bifrost simulation run, but in general, it's something that you can use, you can do with any simulation code. It will be different changes because every code has different units or different convention. But the idea is that the way you do things and the goal that you or the stage that you need to achieve is going to be the same. So I think this class, I hope it will be very, very useful in that sense. Okay, and then today I wanted to go step by step and without rushing anything. So then the idea is that today we basically just transform the atmosphere. We leave everything ready for running a synthesis. But I thought that it could be better to just leave that for the next class. And then again, in the next class, we will do things thoroughly and slowly. So today we just transform the atmosphere, and in the next class, we will do synthesis of a given field of view. And also we will check that during the synthesis, we can do also extra things that are very useful for another maybe studies that you want to do. Okay, so then let me go back, and then as always, we will go to an ideal script. In this case, yes, let me put this here. So we are going to be again in the RH folder and the RH F1D distribution, and in this case, the folder is called Bifrost transform. Okay, so then we are going to go through this ideal script. Okay, so then let's go step by step. So the first thing that we need to do is to download the simulation. And as I said, this simulation is very nice in the sense that it is publicly available, so everyone can download it and can use it. There's no restriction. So you go to this web page that I included here. So it's this one. And in fact, with time, they have been adding different runs that they have been usually published in different publications. So you have several options. In our case, the enhanced network simulation is this one. There's a very brief description here. We will go into details later. But basically, what you have to do is select the run And then you go to proceed to select variables. There's a list here. I will show you later which ones you need for RH. The others are optional, but maybe you want to take a look at them. So imagine that you want to have the temperature. So you just click this box here, and then you go to proceed to select the time steps. In our case, we are going to use this 385. And then you just go ahead, and then it will tell you that there are two options. You can use this one or this one, and then you just download it. Okay, so I will go back just to be here. Okay, so then let's go back to the script. The idea is we are going to use this one. Okay, the name is that it's a enhanced network simulation. We will see later how is the special distribution of the magnetic field. It's a 24 times 24 megameter run with a pixel size of 48 kilometers. Okay. The snapshot that we are going to use is the 385. It's the one that they start offering in the web page, and is the one that has been used a lot. I just cite here some papers, but the truth is that there are much more works that I have used it, and I think it's a good start. For this example, and even for your research, you can use this one. I downloaded the atmospheric parameters that we use for running RH, and I put them in this folder that is inside the folder where the script is. So we have here in this folder, we have we will see it later, but the magnetic field, hydrogen populations, temperature, velocity, and electron density. So everything is there. I will put it on the Dropbox folder, but my recommendation is that you should try also to download, at least for this snapshot, the same atmospheric parameters, just to check that everything is consistent and you can download it without issues. Okay, so I also included the paper that where they explain the run in the Dropbox folder, so you can check it. Just 1 second. Here, so this is the day 8. So this is the paper that I was talking about. And also I included the IRIS technical note that is on the web page. You can download it also, and it's good. You can check it and have an overview of how the Bifrost is run and other things, and what is the meaning, for example, of 385 in the name. So it's a good to, if you take a look at that. Okay. So then I just use this for defining the name of the snapshot. And as I said, I only downloaded the atmospheric parameters that are required for RH. And those are temperature, electron density, the 3 components of the magnetic field, the line of sight velocity, and the hydrogen populations. In this case, non-LT population. So if you remember, we had 2 main components for an atmosphere in RH that were separated. The one that I usually call thermal, and is the one that contains geometrical height, that we will see later how you can derive it from the previous atmospheric parameters. Temperature, electron density, so everything is provided. Line of sight velocity, also provided by the Bifrost run. Then you need it also microturbulence, but in this case is 0 during the run. So we will check later in next week, or in the next class, sorry, if we add a microturbulence or not, but in principle it's 0 when they run the simulation. And also you need hydrogen populations, that in this case they are in non-LT. And you will see in the future that this is not the most common thing, but I believe it's really useful and very nice to have it. Okay. So then this part, it's just provided by the web page. In the web page we visited before, and then the second part, the magnetic part, is also provided because they give us Bx, By, and Bz. The only thing is that if you remember, we needed to provide it in spherical coordinates. So it means that along the way in this ideal script, we will need to transform from Cartesian coordinates to spherical. But it's something that you will see that is relatively easy to do and straightforward. Okay, So then we have basically everything. So the only thing we need to do is to adapt this to RH format. Okay. So then the first thing is to read the files. They are fits files. So in the case of IDL, it's really easy. We just need to use red fits, for example. Here I'm just putting the path where the atmosphere is, the name. I do this sometimes for different snapshots. So I just put it this sentence to make it easy. So if I have more snapshots, I just change the number here, but you can make it easier if you prefer. And then just finish the sentence. So with that, we read that file. But if you see the name is log TG, so it's the logarithm of the gas temperature. So then we need to put it in, I think it's natural, is the name. So put it back in the normal format. So because this is the one that RH will need. So it's a very simple transformation, but just be aware that sometimes simulation groups, they tend to provide things in log format for different reasons. Units, you will see the technical note, but in general, all the Bifrost parameters are in SI units. So this simplifies a lot of things because we basically don't need to change anything. But it's good to always double check that, okay? Then a geometrical height, that as we said is an important parameter. And in this case, it's relatively easy, although not straightforward if you don't check the technical note. So the idea is that it's embedded in the fits file. So the only thing you need to do is to read one atmospheric parameter. So in this case, I'm reading again the temperature, but then at the end, you add this command that is reading the extension. And I think this is also very easy to do in Python. So just be aware that the geometrical height is contained in all the atmospheric parameters, but as it is the same for all the pixels, they include it in this way. That is a very convenient way of doing it because you save a lot of space instead of replicating the same vector for all the pixels. Okay. Then the only thing we need to do here is that for the right 1D atmos, if I'm not wrong, you need to have it in kilometers. So then we just multiply this by 1000. And then we have it in kilometers. And then in the technical note, they also said that Z equals 0 is defined to the height where the optical depth at 500 nanometers is in average unity. Okay. So then if you want to check where I start, I already did it for you. So transform.pro. So then you will see that this index at 79, it's 0. Okay, so then at that height, it's Z equals 0 and it's approximately optical depth unity at continuum at 500 nanometers. Okay, so then let's take a look at the temperature at that height, just to have a feeling if the temperature looks reasonable. And for example, in this case, as it is quite some, if we see, for example, the granulation pattern. Okay, so then I'm going to do a plot. The only thing is that, as I said, the spatial domain, the pixel size is 48 kilometers. So then just to make the plot with the proper dimensions, I added here the scale. And as I think it's better to visualize it in megameters, so I'm just using a scale in megameters, okay? But in principle, it's 48 kilometers. So I just do a normal plot of the temperature at that height, and then I use the scaling factors to just keep the coordinates. So then if we go, if we go to this folder, then well, just let me do this, and then it will stop in 93. Okay. And then we go to temperature. Okay, and this is how it looks, the temperature for the full domain. Okay, it's as we saw before, it's a 24 times 24 megameter simulation run. And you see that in general, everything is dominated by granulation. So you have hot areas that are bigger in size, and then you have dark or cool areas that are narrow, that are the intergranules. Okay, and then this is a good just plotting this, and in my case, I left the bar plot open, so you can see that the temperature is also reasonable. So it seems that units are okay, and also the convention. So you expect this range of temperatures more or less for the quiet sun, okay, at this height. So then we can continue with the line of sight velocity. In this case, it's the same. So we just use red feeds and red feeds. And then just as we said, it's SI units. So we can use the same format. So it's meters per second, what we need for RH. And then just make a plot of the spatial distribution of the velocity. And in this case, I'm adding the color table where we have red, so blue, white, and red. Okay. So then let's see how it looks. Just let me continue. This finishes in 123. Okay. So then the Bifrost velocity A is the one. So you can see how it looks. Again, we have that it is familiar. So we have that larger areas, they have given velocity, and the narrow areas surrounding them, they have a different, the opposite velocity, and the regions between them, they are close to zero or zero, because the velocity is changing of sign. Okay. The only thing is that this color table is the one we usually use for Doppler shift, inferred from observations. So then if someone sees this, it will look like something is wrong, because usually you expect to have red in the intergranules and blue in the granules. But as we said last week, and you will see also in the technical notes, the sign conventions for theoretical studies and also simulation runs is usually the opposite one we have in a spectroscopy convention. So the good thing is that this is the one we need for RH. The only thing is that if you want to make sense of things, you can just do what I did, and is making the same plot, but just changing the sign, just to be sure that things are reasonable. And the only thing is that I forgot to say that as it is in meters, what I'm showing is in kilometers. So I just divide it by 1000. But let's see if we change the sign, if it looks like what we are usually used to have. Okay, so then in the case of this velocity V, now things are natural, I would say. So you have that, in this case, we understand that red means downflows, and they are the intergranular lanes. White is zero, or the change of velocity between intergranules and granules. And then you have the blue, that in this case would mean upflows, is the velocity that is dominating the granules. Okay, so then this one, it makes sense. So then you can understand what is the correct sign, but then be aware that we need the opposite one for RH, as we said last week. Okay, but just as a double check, things are consistent. Okay, so then this is basically what I said, and just that. So just pick the original one, because the one provided in Bifrost is the same one that RH needs. Okay, so then the next one is the magnetic field vector. In this case, we have the three components, so we load them, Vx, Vy, and Vz. Again, everything is SI, so it will be Tesla. So then this is the same format, exactly the same we need for RH. So then here, my recommendation again is to double check things. And for example, if you remember when we used the Muran sunspot simulation from REMPEL 2012, remember that at that time, I mean, in the SER online course, that time we realized that what we usually define as Y was a Z, and then what we assumed that is Z was Y in that simulation. So in this case, if you read the technical notes, the normal or the traditional XYZ convention is the one they follow, but it's not bad if you make a plot and just check that things are as you expect. Okay, so then let's make a plot of the magnetic field. At the same time, also to try to be sure that you are understanding the units. So I'm multiplying this by 1 up to the 4. That is the change between Tesla and Gauss. So I'm putting everything in Gauss, and I'm plotting Bx, By, and Bz. Okay, so then just let me go ahead, and this will stop. Sorry, this was the second velocity. Yeah. Okay, so then we read the 3 magnetic field components, and then let's see that plot. Okay, so we go here, and this is this one. Okay, before I forget, everything that I'm plotting, you will see when reading the script, but maybe I forgot. Everything is at z equals 0. It's just because it's I think it's a good reference, but the simulation goes up to the corona, so you can have different layers, and you can play with you can plot the atmospheric parameters at different layers. But I thought z equals 0 or tau equal 1, it's a good reference. Okay, so then in this case we have that Bz looks like the longitudinal component of the magnetic field. So you have network patches where the magnetic field is pointing to some towards us, and then in the other cases in the opposite direction. And then here in Bx and By, things are maybe what we expect, but I always like to double check things. So now we are going to go a step forward, a step further, and then we are going to just make a plot of this small network patch here, just to check if there's a hint of how Bx and By are distributed, to give us a more confident feeling that everything is as it is, as it should be. Okay, so then what I do is just repeat the plot. In this case, what I'm trying to do is to look in detail to Bx and By, because if you remember from the sunspot simulation, from the Muram run, the magnetic field was radial. So Bx, By, they had almost the same spatial distribution, but they were like shifted. So if you had like white, imagine in this color table, white and black, then the other one was white and black in the opposite. So let's try to see if we can have the same result here for the network patch, because it's also a flux tube that is opening with height. So it's not so different from the sunspot that we had before. So let's see if we can have the same behavior, and then we can feel more confident. Okay, so I just defined the indexes of the spatial region that I want to focus in, and I just repeat the plot, but just picking all those this spatial domain. Okay, so then we go here, then we go back. So in this case, B, you can see that now we are just focusing on this network patch. Okay, and then if you look, let me make a zoom. If you look the network patch, in the case of By, we have like white color and then black color. And then here we have white color and then something here. So it's not as good as in the sunspot, because it was very rounded and very radial. But we can see that it looks like, in fact, this is Bx and By, and the other one is definitely longitudinal field. Okay, so then let's go back. And basically what I want to say here is, it's, as I said, it's not as easy to see as in the Muram simulation, but the truth is that it's not bad. It's not bad to try those things, because you can also get a bit familiar with the features that you have in the simulation. That is something that I would say that is important for the time you have synthetic profiles and you want to understand what they are. So if you have, for example, Stokes V signals, or you have Stokes Q UN signals, if you already have an idea of the magnetic field of a given region, then you can understand if you have or not the expected signals that you will have, depending on the magnetic configuration or the temperature. Okay, so then my advice is simple: just play a bit with the simulation before just jump to running synthesis, because it's always good to get familiar and also to try to understand if there's something that could be a problem or could be not very realistic in the case of the simulation. Okay, so then after that, then let's continue with another atmospheric parameter. In this case, the electron density is the same as before. So units are SI and it's in log scale. So we just need to do the, oh, okay. Yeah, Harsh, do you have a question?
Hi, I am a little bit confused. So in the velocity case, you put negative sign so that it resembles upflow and downflow. So the negative is upflow and this. So my question is, in the BZ case, also it is the same convention. Like, is this positive is upflow for the RH, or
no?
Like, what is the convention? Like, if you consider BZ for RH, what will you call magnetic field towards you? Is it positive or negative?
So you mean what means for RH?
I'm asking the convention of RH of BZ.
Okay, so let me see if I understand the question. So you mean that BZ positive could mean pointing towards the sun or pointing outwards the sun? Is this your question?
Yes. What is the convention?
Yeah, I think it doesn't have an impact, but maybe Han, do you want to add something, or maybe the cat wants to say something? I think it doesn't have an impact on the forward modeling.
Let me ask my assistant here.
Yes.
No, so physically it doesn't. I guess that there is a convention in that one direction would give you a redshift or what is it? One circular component is redshifted or instead of blue shifted. So I'm not quite sure. I think it is the regular convention as everyone else, but so that an up pointing has a certain shift of the left circular polarized component, yes. Which is the general. I don't remember off the top of my head which is which, but I think it is the general convention that people are using.
Okay.
But physically, of course, it really doesn't matter. I mean, it's a convention. What you use for upflows and downflows, it's different, of course. Yes. Physically, an upflow is different than a downflow. Yes. But an upward pointing or a negative, it just changes the polarization sign of Stokes V. So I mean that's the answer.
Yeah. So I think, thank you, Har. So I think the idea is that if you use the wrong line of sight velocity sign, then the radiative transfer solution will be wrong. So you will see that things are messy. But I think the sign of the longitudinal magnetic field will not have an impact on the results. And then depending on your convention or other things, then you can always multiply by -1 your Stokes V signals, for example. But my impression is that there's no impact on the radiative transfer solution if you use one or the other. While in the line of sight velocity, yes. Okay.
All right. Thank you.
Okay. So in this case, you just use the information as it's given in the Bifrost simulation, and then if we want to understand what means inside or towards us, then we can probably check the technical note and we will have some reference there. But the solution of RH will be the same. It will not be affected. Okay.
Thanks a lot.
Yeah.
Thank you.
Yeah. Okay. So then also let's plot the electron density, just because, for example, in my case, I'm not used to know what is or to have electron density as a parameter that I work with. So we can just plot it and see how it looks in the simulation. So in this case, we continue, and then it's 280. Okay. So then if we go to electron, this one, okay. So then you will see that at Z equals 0, it looks very similar to the temperature. But also it's interesting to see that, for example, in the regions where the magnetic field is strong, there are some different pattern respect to the one we have in temperature. So my comment here is just, it looks like the temperature, but if you have time, just maybe take a look at higher atmospheric layers, because you can go like 500 kilometers, 1000 kilometers. And also just check what happens when the magnetic field is strong. So you see big changes in the electron density. So just try to start getting a feeling of those things, because I think it's interesting, and we can learn basically from just playing with the simulation. Okay, and basically that, so just get used to or get familiar with the different atmospheric parameters that we use. Okay, so then I think, yeah, so Harsh, I think you don't have any question, right? So your hand is raised, but can I lower it down, or maybe lower hand? Okay. Okay, okay, sorry. So then let's go to the hydrogen populations. Here we have, as we said before, they are usually given like 6 cases, or they're assuming a hydrogen atom with a 6 level. So then these are N1, N2, N3, N4, N5, and Np. That is the same as we use in RH. And as I said, it's good because it's in a SI unit, so we don't need to change anything, just to put it in normal scale. And also it's in non-NT, so we don't need to change the keyword .input in the future when we run the synthesis, and it's the best we can use. So it's very nice. This run is very nice. Okay, again, in this case, I'm not very familiar with hydrogen population, so just let's make a plot and see how the different hydrogen populations behave in terms of the spatial distribution at z equals 0. I just go like this, and then we read 6, and then it stops here. Okay, so then we go to hydrogen populations, and then you see that it's, again, it seems that it's similar to temperature. It's true that N1 is a bit different, but still it seems that the pattern is mainly granulation pattern. So we can see again strong relation with temperature, and also again you can see that there's a deviation from what you would expect in the color grade in the regions where you have magnetic field. Okay, so then my advice again is to continue looking at these things and try to also make or try to understand why these things are happening. Maybe it's interesting for you so to see why the magnetic field can impact on the hydrogen populations, and the same why the temperature is mainly the one that is given the spatial distribution of the hydrogen population. Okay, so then up to this point we have read everything that we need for RH, and then we need to do a few more extra things. The first thing is not mandatory, but I strongly recommend it, and is to, I would say, tailor or just modify or cut the vertical domain, because the simulation goes from very deep up to the corona. And the truth is that for chromospheric lines like calcium, magnesium, or sodium, that they sometimes are upper photospheric or chromospheric. So you don't need definitely the corona, and also you don't need probably the transition region. So then I would say that you may cut, or you should cut the upper part of the atmosphere, because you are not going to need it, and then, or use it, and then it will save computational time, because if you have less points in any direction, it will be faster. But also it's true that sometimes things in complex layers like the transition region or the corona, so the atmospheric parameters could behave in a very complex way, and these even if it's not affecting to the solution of the calcium line, it could affect to RH in the sense that it could make it crash. So then you save time, but also you may save a possibility of that a bad pixel makes the code crash, and then you lose the solution in that pixel. but not because of a calcium atom. It's because that something went off in some region where RH is sensitive, but not the transition of interest. Okay, so then my advice, just cut it in a reasonable region. In this case, I'm proposing from -1000, that is in fact very deep, but just to be in the safe side, up to 3500. That also is very high in the atmosphere for calcium infrared lines, where they in average form between 1000 and 1500, but just to be in the safe side. The important thing, and I said it here, this please, it's very important, and then you should check it depending on your transition. So if you are going to use UV lines like Lyman alpha or beta or magnesium 2 H and K, you definitely need to go up, because they are sensitive to the transition region that in average is higher than this. So just tailor this height domain, but based on your interest and depending on the spectral lines you are going to synthesize. Okay, so then based on that, I define an index where I'm going to cut the atmosphere, but I keep the full spatial domain just to have it for later, and then in the next class we can decide on the go to just focus on a small region. But in this case, I will save everything. Okay, so then it's just keeping the same atmosphere but reducing the vertical domain, and then with that we have everything in a small, so in an optimized package, in the sense that we moved from this size with 496 points in the vertical domain to 173. That it's a reduction factor in speed and also in the volume that you need. So I think it's good if you spend some time working on this to define the best vertical domain for you, or for your transition of interest. Okay, now as a note, just remember that we are cutting also from the lower part. So now our z equals 0, it's in this position. So we've got this. This print is giving us 0. Okay, so then the next step is the magnetic field. Also, as we are going to transform the magnetic field, if you reduce the vertical domain in the previous step, then this step will be also faster. And the idea is, you remember, we need the spherical coordinates. So then what we need to do is we can run a loop that is covering all the spatial domain. So this I and K will go X and Y. And then we compute the field strength as the square root of the square of all the three components. Then the inclination is derived this way. Okay, so this B is computed in the previous sentence. Then you have it already. And then the azimuth can be obtained like this. Okay, so then basically with this loop, you are already transforming everything to spherical coordinates. And as this was already in Tesla, sorry, this one was already in Tesla, the output is also in Tesla. And the output of this computation in IBL is also in radians. So then you have everything in RH format. So there's no need to additional transformation. Okay. But as I'm always certain that I'm making mistakes in every sentence, then let's double check that the output is reasonable and compare it with the previous plot. So then in this case, I will have two rows with panels. The first row is Bx, By, and Bz from the original plot, but only in the network patch. And then the second row will be the field strength, the inclination, and the azimuth. Okay, then let's go there. This is a loop. Sorry, it will take some time, but just forget about it. I have already the result here, and then this is how it looks. Okay, so if you start with the module of the field strength, you see, well, look at the color table. So white is 0 and black is strong field. So then you can see that the network patch is here, and then some small concentrations of magnetic field, and they are correlated with the longitudinal field that we have before. although here we have different signs because it's weighted with the cosine of the inclination. Then if we go to the inclination, we can see that this is 180. So the magnetic patch is it's very vertical, and also the other magnetic patches. And then we have a mix of polarities that is it's expected on this complex simulation. But in general, you can see that in the places where the magnetic field is strong, the network patch, they are very vertical. Okay, and then the azimuth, in my case, it's always difficult to make a sense of it. But if I see something like this, I would say that it looks okay. So with this pattern that is complex. Okay, so then it looks like the transformation was correct. So then we can continue. And then the next step is, I said, inverting the atmosphere. So the idea is that, if you remember, in the previous class, we said that the first index of each atmospheric parameter should be that atmospheric parameter in the top boundary of the atmosphere. And in the case of Bifrost, of this simulation, if you go to the technical note, they will tell you that it's the opposite. So we need to reverse that. And in fact, I put here a history note just to make things maybe a bit more funny. And they explicitly said that in this run, so they say it here. And what they basically said is that in the previous Bifrost run, it was the opposite. And I think this is because it is heritage of multi, and as we said, RH is using that convention because it's heritage of multi. So just as interesting thing and maybe a side note. Okay, so then in our case, with this simulation run, let's reverse the axis to have everything as RH needs. Okay, so then in the case of the geometrical height, we just do it with this ideal sentence. And then in the case of the rest of the atmospheric parameters, we are going to do it pixel by pixel. And the only thing is, I will use the opportunity to create an array of hydrogen populations with the same format that we are going to use later with the RHMD ideal routine for providing the atmosphere to RH. Okay, so then it's very simple. It's a loop like the previous one. We are just reversing the temperature, the line of sight velocity, electron density, field strength, inclination, and azimuth. Then we do the same for the hydrogen populations, but then I save it this way. So it will be an array of X and Y, so the spatial domain, then the vertical domain, and then 6, that it will be the 6 hydrogen population values. Okay, and then with that, we can finish the loop, and we have reached the end of the script. Now we are going to enter in the summary. And the idea is that I usually prefer to keep things separately. So then I usually run this in one folder. I save it like an ideal save file. And then I run RH in a different folder calling to this atmosphere. So then in my case, I prefer to keep things separately. So then we just save it, and then we have it ready for any computation you want to do. If you want to run calcium, you call this. If you want to run sodium or potassium or magnesium, you call this snapshot, and then you can use it. If you want to have different lines, remember that the height domain needs to be updated. But every photospheric plus chromospheric line, you can just call this and it will work. Okay, so then before going to the summary, is there any question of the process?
Yeah, I mean, you explained that that Z equals 0 is the height where tau equals 0. This is the average tau, right? So
yes.
If you normally would look in every pixel, the height, the geometrical height at which tau is equal 1 is at a different height
yes.
normally.
Yes.
So when you make like a crosscut of the magnetic field at Z equal 1, this is at the average height, the average geometrical height,
yes.
where tau on average is 1. It's not I hope people understand the difference.
Yes.
I just wanted to reiterate and make that clear.
Yes, thank you. Yes, and in fact, one of the exercises we will do in the next class is when running RH. RH is computing already the optical depth and also the optical depth at 500 nanometers. So we are going to save it, and you will see what Han has already said. So if we picked a fixed index in the geometrical height, so for example, z equals 0, you will see that the optical depth is moving up and down. So it's an average, but it could, in one pixel could be log tau -1 or -1.5, and another pixel could be log tau 1 or 2. So we will see that, and yes, it's true that this is not a fixed optical depth, it's a fixed geometrical height. Okay, so additional questions or comments? No? Okay, so then summary, we started from Bifrost simulation run. It's a one that is publicly available, so feel free to use it, and I recommend you to use it because it's very, very nice. And in my case, I always found that in general, things are okay, are reasonable. We downloaded the snapshot. We started just reading the files and then checking that we have the correct units. Then we also check the velocity sign. We understand that the one provided by Bifrost is the one that RH needs, and is the opposite that we usually obtain, for example, when we compute a Doppler shift of a spectral line. And then we transform the magnetic field from Cartesian to spherical coordinates. We also reduce the vertical domain. And as I said, the main driver is reducing CPU time because you don't need the extra points in height up to the corona. But also, as I said, sometimes things could be very, very complex in the simulation and could make RH crashing. And you don't need it unless you are already focusing on the corona. So missing some pixels because the code crashed is something that you just avoid cutting the top boundary of the simulation. Then, as I said, RH needs the first index to be the top boundary. So then we just inverted the atmospheric parameters. And with that, we had everything ready for running RH. And I save it in an ideal file. You can do the same with Python probably. And then what remains to do is just in the next class, what we're going to do is, okay, just 1 second, Harsh. So what we're going to do is to take the configuration from day 7. And remember that this was the last class where we finished configuring the non-LT part for the Carlsson line with a specific Q-core and Q-win and wavelength point definition. We also work with the Kulux line list to provide the satellite lines in the Carlsson 8542. And we also work a bit improving the atomic parameters in terms of log GF and also different coupling schemes for the transition. So with that very complete configuration for the Carlsson line, we are going to run the synthesis with the today's simulation run. So then I hope everything will work, and then we will see it in the next class. Okay, so that before that, I think Harsh has a question.
Hi.
Yes.
So basically, hydrogen populations are given basically 1, 2, 3, 4, 5, and the 6 is the, I think, continuum when the proton population, right?
Can you repeat again? Sorry, I didn't.
So in the simulation,
Yes.
there were 6 values given for hydrogen population.
Yes.
That is 1, 2, 3, 4, 5th level, and the 6th is basically continuum. Basically, it is considered 6th level atom.
Yes. Yes.
I understand that.
Yes. Yes.
So, and if you browse RH code, there are other levels like H10, H9. If you want to use some other hydrogen atom given in RH, so you cannot use this simulation. Is it correct, or is there some way we can transform this 6th level population to some other level population? So in RH code, in Atmos F folder, there are many hydrogen atoms given.
Yes, but I mean, if you are solving and Han probably will confirm, but if you are solving hydrogen in non-LTE with any atom, I think those populations will be updated because you are solving hydrogen in non-LTE. So then it means that even if you are providing them in the atmosphere, internally, the code will solve a non-LTE atom. It will solve the populations as well. And those are the ones the code will use.
Okay.
So
Yeah.
if you use, so there are two things. Hydrogen is needed in the background to calculate some of the continuum opacities. For instance, the H- opacity. So initially, when you read in with an atom that has more levels than the 6 that you provide in the Atmos, then it will populate the first 6, the first 5, plus the protons, and leave the set the additional levels, 7, 8, whatever, how many you have, to 0. And that atom is then used for the background atom. Now, if you try to solve hydrogen in non-LTE with a larger number of levels, then the initial solution will just be the one that you set in the .atoms file, namely either a 0 radiation field or LTE population. And that initial solution will be independent of the solution from the atmosphere.
All right. Thank you.
Yeah, so there should be no problem if you use an atom that has more levels.
Okay. Thanks a lot.
Okay, thank you. Yeah, I think there's another question, Dato.
Yes, Carlos, so are you going to run this simulation in the next class using 2D RH or 1D RH in parallel?
Yeah, first will be 1D serial, so it pixel by pixel.
1D serial.
Yeah,
okay.
just in ITL, just to let people know how to do it, but it will be always 1D. And then in the future, we will do it in parallel, but it will be the same 1D. So I'm not running 2D or 3D. So why?
So in principle, it would be, I think Carlos will limit himself to 1D because that is basically what we will do once we do inversions, right? So it goes a little bit beyond the intent of this course.
Yes.
In principle, it's very possible and almost straightforward to populate a 3D model for RH with the simulation and do a true 3D simulation solution.
Yes.
In very much the same way. But in this case, in the context of this course, we will just do the column by column solution. So what is called 1.5D in normal parlance.
Okay.
Yes.
Thank you.
But Dato, can I ask what is the so why I just
no,
to continue
I was,
with the, yes.
I was just thinking about if you can take this atmosphere and do everything in, for example, 2D RH. I've never used 2D RH or 3D RH.
Okay, so then the answer is because I have done it in 3D with this snapshot. So if you take the full snapshot, you can run it in 3D with RH, and I have done it for Carlsson. It's something that is work in progress, but is something that is a bit tricky. So it's really far from this course. Also because eventually we will move to this side that is also in version 1D. But if it's something that you are interested on, we can work on that because this snapshot, in fact, it works with RH, and also Han have done some tests. So in principle, if you prepare everything in the proper format, that is not the same as this one, it's a bit different. The snapshot behaves okay, and RH also behaves well, for example, for calcium, including polarimetry, and you can get 3D. But it's true that this is a different task and also requires a proper computer while running things, mainly because memory is shared in RH or non-shared. I always shared, right?
So, shared.
Yeah, so depending on the number of wavelength points, you may need between 1 and 1.5 terabytes of RAM memory. Okay, so then this is very far from this. But the question of if it's possible to run 3D with RH and with this snapshot, is yes. Yes, I have tried. Okay.
Thank you.
Okay, good. Okay.
So,
Okay.
I have a question.
Yes. Yes.
So in the line of sight velocity maps,
Yes.
which showed like any color scheme, like doesn't matter whether what is upflow or what is downflow. So
Yes.
physically we know that at the center of the granule cells it should be upflow, strong upflows, and in the intergranule lanes it should be downflows. But here in these images I see at the center of the cells mostly it's not strong upflow, whereas the strong upflow or downflow both are like intergranule lanes are clearly strong downflows, but the strong upflows are also at the edges of the
Yes.
granules.
Yes. Yes. I think it depends on but my impression is that the material goes up and then it starts to accelerate towards the edges. So I think it's not so strange to see low line of sight velocity on the center of large granules.
Okay.
But, but maybe Han, you want to, because
yeah. So what happens is the upflowing material cools radiatively, and so in the center of the cells it then stagnates, and that's why you see mostly zero velocities there. Because at some point the upflow can no longer be sustained.
Okay.
And so yes, you'll see. It's a good observation that you'll see the highest upflow velocities at the edges of the granules, not in the center.
Yes.
I mean, the granulation is the typical picture that we have of granulation is a bit simplified. It's not the picture that we see in these simulations.
Yes. I think, Nancy, for example, one good exercise, if you have time, is to download also, because the simulation provides the 3 components of the velocity field. So you can download the horizontal ones and take a look, because my impression is that, as Hans said, it's basically no line of sight velocity in the center, but then I think the horizontal velocity you will see that it's getting accelerated until the edge, and then you have the strong downflow.
Okay.
So
also be aware that the if you do an observation and you would plot the velocities, it is actually the velocity measured more or less at tau equal 1 in the line. Right, which is not the same as the velocity at one geometrical height. So there's a difference in appearance that you get from that as well.
Yes.
And you would have to think. You have to think very carefully on how that works out, and if you can understand that. But there is the appearance of this image is very different than the appearance that you would see if you make a Doppler graph.
Yes. Okay. Yeah, I think we can do that. It's a good idea. So next week we will compute the optical depth unity. So then we can make an extrapolation or interpolation of the velocity field to obtain every pixel on the velocity at every pixel of optical depth unity, and we will remake this figure maybe next week or in 2 weeks. But I think it's a good thing that you mentioned, Han, and also Nancy's question. So we will do that. So we will remake this figure, but at the optical depth 1 instead of at z equals 0. Okay. Good. Okay. Thank you for that.
Thank you.
Yeah. Okay.
Hi, so just one last question.
Yep.
So basically, it's a follow-up to last question. So he asked that. About RH3D. So I wanted to ask, the RHST3D folder does actually 1.5D approximation, or it actually calculates the atmosphere in 3D?
Can you repeat again, because I couldn't follow well? So you said
in the RH,
yes,
the folder is RHST3D.
Yes.
So that the 3D folder actually calculates the atmosphere in 3D, or just calculate in 1.5D approximation? Like column by column.
That's a true 3D solution.
Yes.
All right.
Yes. So in the 1D we have 1 pixel, and we assume that everything is so the atmosphere is just 1, and in 2D you have the effect of the pixels in the different side of the given pixel, and in 3D, this is full 3D. So I mean, each pixel will see the effect of the surrounding pixels. Okay.
All right.
And yes, and for this reason, I was saying that the computational requirements are very high, because you need to have to load, in the case of RH, the information, not only the pixel that you are actively solving, but also the pixels surrounding it, because they will affect. And this should be solved iteratively, so things become a bit messy. But yes, it's a full 3D, and I think the best we could aim for in radiative transfer.
Thank you.
Okay, but please be aware that 1D is really complicated,
Yes,
and so we could jump in the future. Maybe in 1 year I can explain you how to do it, but it's something that you will spend more time on configuration and just making the test run than analyzing the output, because it will take 1 day or 2 days just to realize that it crashes, and then you need to look for the issue. So that is a different topic. Okay, but I'm seeing that people are interested in it, so I will think about it after the desired course, and maybe we can make an extra or expansion of this RH course where we work on that. But this will require asking for time, and okay, Nancy also seems to be interested in it. Okay, I took note. I take note of that.
You.
But that the truth is that I need to really run it again and be sure that it works, because it's tough. But we will do it. Okay, I take note of that. Thank you for the feedback.
Thank you.
Okay.
All right.
Okay, thank you. So then basically I finish here, and yes, so then let's go back. Oh, sorry, the presentation is here. Okay, so then homework is, as always, try to run the test I prepared. Try to download the snapshot from the University of Oslo webpage. Then follow the steps in the ideal script, and just check that everything looks okay. You don't have any issues. And then this is just an advice, but maybe it depends on your time. But I would say that you should try to just say, okay, I have everything that it seems that is needed for the synthesis. And in the previous class, we learned how to use write 1D and read 1D to prepare everything for RH. So try to create an atmosphere, the Atmos part and the .p part with everything that I gave you. I would say that it probably may not be straightforward, or you may have some issues and you said, oh, why the profile is completely flat, something like that. But the truth is that it probably will be a minor issue. And then next week, when we see how, next class, when you see how I do it, you would probably say, oh, I understand now. And then you will always remember, or you will remember it forever. Okay, but it's just as an advice. So if you have time, then give it a try, and if not, don't worry, because we will cover it in the next class. Okay. Then next class, I said it several times, configuration from day 7, that I think is one of the best configurations that we could have for the calcium 8542 spectral region, with the Bifrost atmosphere that we already have in the RH format. We will run it over a small field of view, and you will see that things take some time in serial, so you will see the benefits of using a parallel wrap, but still it's a good way of, so I mean, it's good to know how to do it this way, because sometimes it's good to just pick 1 or 2 pixels and then focus on them, and having this script will allow you to just do that quickly and check that the profiles that you get, they have the proper Doppler shift, they have the proper polarization signal, something like that. Okay, so it's not bad to have this as a just test option. Okay, then the next class. And for this reason, I've been saying several times next week, but then I changed to next class. So, so I want to propose to have the meetings every 2 weeks. And the reason is that I have a lot of things to do these days after summer. So I want to prepare things carefully, because as I said at the beginning, RH, it's much more powerful, but it's also a bit more complicated. So things need more double checking from my side. So I want to do it carefully. So 2 weeks, every 2 weeks, I think is a good period. And also it means that we will extend the period for covering the RH online course and the design. So we will see each other for a longer period. So then next class will be in October 1st. And before closing, is there any final question or comment? No? Okay, so then thanks a lot for joining us today and enjoy the weekend and also the rest of the week. And then just let me stop sharing. And yes, thanks a lot and see you soon.
Thank you.
everyone.
Bye.
Bye.
Thank you, Carlos.
Bye.
Bye.
Thank you. Bye-bye.